Torque on a Playground.
Presented by Matej Jackson and Jacob Hanau. The big idea of our project is torque.
The torque produced by a force exerted on a rigid body about a chosen axis of rotation is equal to force times length times the sine of the angle of the force.
When an object is in static equilibrium, it is either at rest or at constant velocity. For an object to be in static equilibrium, its forces in all directions must add up to zero, and its torques need to add up to zero. These are known as translational equilibrium and rotational equilibrium, respectively.
In this photo, I am standing on one side of the seesaw while two dumbbells are on the other side of the seesaw. Although I have a greater mass than the two dumbbells combined, the seesaw stays balanced because the dumbbells are further from the center. So here's the math of the scenario. My mass is 67.5 kilograms, and the dumbbells each have the mass of 18 kilograms. We can assume that they are one object, so the two dumbbells together is 36 kilograms total. We decide to place the dumbbells 1.45 meters from the center of the board. Now we must calculate the distance I should be from the center on the other side. We know that the net torque must equal 0 and that the torques of the board on each side are equal. We can cancel out both of these torques, then set up the equation as weight of the dumbbells times their lever arm length equal to the weight of myself times my lever arm length. As seen, we can simply solve for L2, which is about 0.77 meters. Now we're going to talk about what static equilibrium looks like in a moving object. Here we can see the merry-go-round moving at constant velocity. Since it is moving at constant velocity, we know that it has static equilibrium. Obviously, there is friction from the axle working against the motion of the object, so it truly is accelerating in the negative direction. However, for this experiment, we will assume there is no outside torques acting on the merry-go-round. Referring back to the definition of static equilibrium, this object has net forces in both directions equal to 0, and net torques equal to 0, so it maintains static equilibrium and therefore moves with a constant velocity.
Now we are going to talk about a situation where the object is not in static equilibrium. Looking at this diagram, the object has 4 different forces that act on it, creating torque. The dumbbells are the same weight but at different lengths, and the torques of the board are at equal length and weight, so they will simply cancel out when calculating torque. Mathematically, we can calculate the actual torque in Newton meters. The two counterclockwise torques are positive and the clockwise torques are negative. Obviously, the torques of the board cancel out. However, the lengths of the dumbbells are different. The length of the first dumbbell is 0.98 meters from the center, while the other length is 1.14 meters. As seen on the screen, we can set the difference equal to the net torque, which comes out to be negative 28.28 Newton meters. This means that the object should rotate clockwise, which is in the negative direction. Let's watch and see. Clearly, the object is rotating clockwise, which is the negative direction, as seen in the diagram.
One component of calculating torque that is very important is the angle of the force. All of the forces seen so far have been at 90 degrees to the board. Sine of 90 is equal to 1, so it does not change the torque. However, that is not always the case. Here are two examples of objects with 0 torques acting on them, even though they have forces applied to them. Here is an image of me pushing on the seesaw at an angle of 0 degrees. Sine of 0 is equal to 0, so the torque of the object automatically becomes 0, regardless of the length and the force applied. Example 2 refers to the merry-go-round with me standing on top. Here's a top view of the object. Multiple forces are seen acting on the lever arm, and these would all produce torque on the object because they have components acting in the direction of the object's motion. However, when I stand on top of the merry-go-round, there are no components to my force that act in the direction that the object rotates, so there is no torque produced and the object does not move.
During our project, we encountered various sources of error that skewed our data. Because the playground we were at was next to telegraph, we were getting a lot of wind that added additional torque to the experiment, causing the seesaw to not stay completely at rest when we wanted it to.
The second form of error that we encountered was the wobble and sliding of the board. The fulcrum we were using was broken, so it did not hold the board in place as shown in this video. However, later on in the experiment, we noticed a new set of seesaws that were connected to the fulcrum better. Lastly, in our experiment, we talked about a merry-go-round moving at a constant velocity. However, it was truly slowing down because of the negative torque that friction had on the object. To fix this, we could simply put oil on the axle and the opening in the merry-go-round. This would virtually eliminate all torque and make the object move fairly close to constant velocity. This presentation showed just a few examples of torque and static equilibrium working in real life. We hope you enjoyed and we thank you for watching.